Hello, and thank you for joining the Thomas Expert Series. We're going to get started in just a moment. In the meantime, I would like everyone to please mute their microphone as they're joining. This Expert Series is recorded and will be placed on demand, so please let your colleagues know how much you enjoyed the presentation today. So get everyone started and familiar with the chat. Where is everyone tuning in from today? I see Vanessa's from Texas. Ooh, Jersey, Vancouver, Atlanta, cool. North Carolina. Awesome. Oh, we got San Francisco. At this time, I'm going to turn it over to Casey, the fume hood product specialist, here today to talk about chemical fume hoods applications for exposure control in the lab.
Thank you. Yeah, as she said, my name's Casey Fulmer. I am a fume hood product specialist, and I'm going to talk to you guys today about fume hoods and applications for exposure control in labs, and the process involved in going through the fume hood selection process, whether you're helping someone do that or you're doing that themselves or yourself. It's all applicable there. We're going to talk about what a fume hood is, just defining that. Talk about whenever you hear the ever specific "I need a hood" comment, and then we'll discuss all the different things to consider whenever selecting a hood, making sure the right one is placed in your lab or your customer's lab. So starting off, what exactly is a fume hood? Well, it's a ventilated enclosure where you can handle hazardous fumes, vapors, gases, aerosol, and non-hazardous dust safely. You can handle all of that. It captures and removes those contaminants and exhausts them in some fashion, typically outside, above the building. And these fume hoods offer operator or user protection only. If you're looking at that image, the user is on the left side of that profile of a fume hood, and the way it does this is simply by moving the air through it. They're typically connected to an exhaust duct work, a system, a series of duct connections, and then exhausted to the outside via an exhaust fan, and then the fume hoods are aerodynamically designed so that it does so very efficiently, and keeps everything inside of it. Before we get too far into it, I want to review some terms that are very, very common. You may already be familiar with them, but just in case there's anybody on the call, I always think it's important or valuable to cover what these mean, because I use these terms pretty often. First is phase velocity. Phase velocity is the speed of the air as it's entering the fume hood. It's measured in feet per minute. So if you think of your car, and when you're driving, it's measured in miles per hour. It's a similar concept. Speed of the air over a distance, basically. And then airflow is a common terminology for the next definition, but it's it's better related to a term of volumetric rate. So it's actually the rate of the air, the volumetric rate of the air that's exhausted through the hood at any time. So instead of being just the speed of the air, it is how much air that is moved through the hood over a period of time. It is measured in cubic feet per minute, or CFM. If you hear anybody asking, or a mechanical engineer who's requiring the airflow for their hood, well, they're talking about this volumetric rate, and they're just using that to design their buildings. Also, sash height, which is just the area of the opening, how high the opening is on the front of the hood, and that's just a design criteria, what the user is planning on operating the hood. And all of these are related through an equation, Q equals V times A, where V is phase velocity, A is area of opening, and Q is the volumetric rate, or CFM. So if you think about it, phase velocity, feet per minute, area is feet squared, so there's 3 feet per minute, that's cubic feet per minute. So now that we have all of that reviewed, I want to get to a point for a request or a comment that I get often, and that is, I need a hood. And this is kind of a problematic generality, because a hood can mean many different things depending on what you're doing. I know that people work in clean benches and they call them hoods. Clean benches, they only provide product protection. So if you were to send a clean stream of air from the back of the unit towards the front, just making sure that whatever's on the inside remains uncontaminated, and all of that is pushed towards the user. So it needs to be non-hazardous. So it's only providing protection for what's on the inside, not for the user. We know that people who work in biological safety cabinets, or BSCs, call those hoods. And these are different because they offer both personnel and product protection. So if you need a product to remain in a clean environment on the interior while also having an inflow of air to protect the user, then a biosafety cabinet is what you would need. And then we have what is typically referred to as a hood, in a fume hood. And like I said, fume hoods offer personnel protection only, because all of the air that's coming into the hood is moving away from the user's breathing zone, and it's taking whatever's on the inside and exhausting it, making sure that the user never comes into contact with the vapors that are on the inside. You're not getting any kind of product protection, because whatever is in the atmosphere of the laboratory is now coming into contact with what's on the interior of that hood. So it's personnel protection only, and is the type of product that we're here to talk about today. The important note here is that these hoods are not interchangeable. If you were to have an application where you were handling hazardous drug powders, and you were to use them and you said, I needed a hood, and somebody provides a fume hood for that application, well, those particulate does not dissolve in the atmosphere. It does not disperse in the atmosphere. So you would just be exhausting that hazardous powder to the top of your building, creating a high probability of exposure to that drug, whether it was.
I'm just listening to the webinar. What's up?
Sorry, yeah, a little distracted. I'll keep going. But and similar, if you were handling some biomaterial, again, that does not disperse whenever you exhaust it. So identifying the right product is very, very important. So fume hoods, if you're using a vapor, gas, fume, aerosol, anything like that, fume hood is very likely the way to go. And there's a lot of things to consider in your fume hood selection, and we'll cover those next. We have things like materials of construction. What should the hood be made out of to accommodate all sorts of applications that come in are taking place inside fume hoods? Is there any heat involved, and considerations associated with using heat? It's very common. Addressing the building mechanical system that is present on your building, making sure that the hood is set up to work with that. And then application specific fume hoods. And the reason why I'm covering all of these is because applications in fume hoods are extremely vast. It's hard to pin down one specific application, but working through these considerations can help any user, make sure that they're safe in the process that they're doing, and that's the goal of having a fume hood, is making sure that the user is safe. So let's break those down a little bit individually. We'll talk about the materials of construction first. There's all sorts of materials of construction of fume hoods. We're going to talk about a few main ones that you'd see in the industry today. The first is epoxy coated steel, and that is a very basic type of liner. It's exactly what it sounds like. It's got an epoxy, which is chemically resistant, but it's coated over steel, and steel is not typically very resistant to acids or corrosion. So if you are using solvents or very mild acids, this might be a good option for you, because if you're using solvents, one of the more chemically resistant materials might be a little overkill and more expensive than you need in your hood. So the epoxy coated steel could be an option. The reason why you wouldn't want to use those acids again is because if that epoxy coating were to chip or break or something bubble at some point in its life and expose that coated steel or that raw steel, then you will eventually corrode the entirety of the interior of the hood. For those applications, there's a much better material of construction, and that's fiberglass reinforced polyester, or FRP. If you see that acronym, it's talking about this material, and the reinforced polyester is very chemically resistant material that is both resistant to solvents and harsh acids. We have applications where we know that customers are using very, very volatile acids, and those are compatible with the FRP. And solvents have no effect on them as well, making this a great one-size-fits-all material for someone who might be using, broad chemistry with many different materials or chemicals. It's the industry staple. Pretty much every manufacturer offers a version of this FRP. So again, if you're using a broad range of chemicals, or believe that in the future your chemistry might change, this would be a good one to explore because of the broad compatibility of it. In certain applications that we'll discuss in a little bit, you would potentially have a need for a hood that has stainless steel on the interior. Stainless steel offers a solution that is extremely easy to be cleaned, especially when they're welded in place. Those coved corners make it very easy to get in, wipe it down, make sure that there's no acids or chemicals corroding the material constantly. And it's also very resistant to heat. Obviously, if you were heating something, whatever that something is, if you were to burn, melt, or warp your liner, it could potentially compromise your fume hood. So stainless steel hood is very conducive to handling heat application because it has high resistance in those factors. You just want to be careful, because sometimes you have a customer that hears 304 or 316 stainless steel, and they think, oh, well, yeah, that's a great material. It's probably very resistant to all sorts of things. It's a one-size-fits-all material, and that's not really the case. Things like hydrochloric, sulfuric acid will dissolve or will digest that hood over time. So just be very careful, making sure you address that potential hazard in the selection of your hoods. With those harsh acids, there are other materials of construction, including PVC, that have excellent compatibility with very volatile acids. So if you're using potentially a high quantity of acids, and your acids are very, very volatile and used for digestions, then a PVC might be a great option. The only downside with PVC, obviously, is it does not have very good heat resistance, and it's not very compatible with solvents. So if you have a lot of heat, you need to make sure you accommodate that, and solvents would probably need to be in a different material. And obviously, these are only a few of many materials. I know that there are many out there. These are by far the most common materials that you'll see. So it's knowing these gets you in a great position to make sure that your hood is set up and built to last with whatever you're handling, whatever your processes are inside of it. The other thing to discuss or to consider is, will there be heat in your application? And I know that this is actually a very common thing, or oftentimes heating things in their chemistry and in their science. And generally, heat can be mitigated pretty easily, but occasionally there can be a problem where there is too much heat in a fume hood. And that is because eventually, if you have too much heat inside of a fume hood and you have a certain amount of airflow that's flowing through the hood, and if the heat is such that it is greater than what can be diluted by the incoming air, what will happen is, as that heat is not overcome, it will create a greater, more and more pressurized portion in the upper portion of your fume hood, and eventually that heat will build a pressure big enough that it might potentially burp containment. There will be partial loss of containment through the upper portion of the hoods. That's because fume hoods in the marketplace are bypass fume hoods, meaning that there is a little bit of an opening above the top of the sash. So if that pressure becomes too great, then you might lose containment out of the top of the hood. So it's very important that this is considered, especially if you're using significant heat. It's okay though, because just because there is a problem does not mean that there's not a typical solution. What you can do is you can simply increase the volumetric rate through the hood. A larger amount of air moves through a similar area. You remember the Q equals VA. If you increase your Q through a constant A, your velocity will increase. So if your velocity is faster, if the air moving into the hood is faster, it will be harder to be overcome by the heat, by the pressure that's built up. It will also be more effective at diluting the heat that takes place inside of the hood. So increasing the volumetric rate through the hood is a possible solution. You might need a larger hood if you have a need for or if you're planning on using a 4-foot hood, but using a lot of heat. Well, it might not be a bad idea to look at a larger hood, like 6-foot or 8-foot, because a larger volume of air on the inside of the hood means it is harder to get to a concentration of heat that is too great. That heat will be diluted and dispersed amongst the greater interior of the hood. That could be a solution. And then if all else fails, you've lowered your sash, you've increased the airflow, you've considered a larger hood, and you're still using too much heat, it might be time to consider an alteration to your process, a reduction in the process, a multiplication of your process, doing these in different hoods, multiple hoods, things like that. If you have too much heat, eventually the risk of the exposure becomes greater than the desire to not have multiple fume hoods or maintain your process. So that is something that can be considered, and I've talked to many people who that has had to be the route, their solution. And then, as I mentioned a little bit in the previous slide, there's a material problem with heat. If you are using a lot of heat, PVC will warp and or melt, especially if you're using a hot plate and you're heating samples up really, 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 really hot. We know that sometimes in a lot of applications, this heat is greater than 400 degrees Celsius. It is very, very hot. PVC melts at 60 degrees Celsius. So it's not a very high threshold to break. To break. So if you have heat right next to the liner, it will start to warp it. If you have really hot samples and you set it on your work surface, it will burn it immediately. So making sure that if you chemically need a PVC hood to be compatible with your materials of construction and you are heating things, you need to make sure that there's a way to accommodate those hot samples, like an epoxy plate or a ceramic plate, something that insulates heat very well, that you can set those on instead of burning your beautiful, expensive work surface. Things to be very aware of, for sure. The next thing to discuss is the mechanical system that is going on. There's a few kinds of mechanical systems, but the most common type of mechanical system that fume hoods are placed on are either CAV or VAV. So CAV stands for constant air volume. So the airflow through the hood never changes. No matter where you have your sash position, your airflow, your volumetric rate remains constant. Aha, see, that's where the name comes from. So if you have that constant in your opening and closing the sash, your face velocity would change through the entirety of the sash, with the lowest point being entirely open and the highest point being just before close, simply because the area is changing. This is very common for low quantity of hoods. Anything less than 5 fume hoods would likely be found on a constant volume system, because the other types of mechanical systems are just more expensive to install, and the return isn't seen as fast with fewer hoods. The main thing to consider here is the type of hood. It just needs to have a substantial enough bypass opening above the top of the hood to accommodate more air as it's closing. It's not an uncommon material or form of construction to have that type of bypass opening. The other type, as I mentioned, is a VAV, a variable air volume fume hood. So this, or mechanical system, this system modulates the airflow or volumetric rate as it's going through the hood, depending on where your sash height is. If it's fully open, your mechanical system will ramp up to make sure the airflow is such that your volumetric rate is such that your face velocity is maintained throughout all of the range of the sash. If you lower the sash, that volumetric rate will decrease, again, to maintain a face velocity. The things to be aware of here is, if you have one of these hoods, you need to make sure that it can accommodate that type of system, meaning it would need a restriction in the bypass. But it also, those systems require more complex controls and coordination with the building that need to be accounted for. If you have a VAV system and you plan for a hood that is not designed to be put on that, you could be in a really unfortunate situation. So just be aware of what you have. Also, if you have a mechanical system that has a, let's say, old supply air system or exhaust air system, you might find that you have limited supply or exhaust capacity. So if you have an existing lab space and you've decided that you need a fume hood, you need to make sure that your exhaust system is set up to be able to increase to accommodate that extra exhaust that's being taken out of the lab. But at the same time, even if you have that capacity on the exhaust side, whenever you take air out of the lab, you need to then supply it back to the lab. So making sure that your supply air, your makeup air system, can then accommodate that increase of exhaust to replenish that lab is also important. And you might find that you are kind of constrained, that the amount of air that you have is limited, and you might need to consider a hood that can operate with a lower exhaust rate, such as a high performance fume hood, which is a fume hood that has excellent containment properties at reduced face velocities. Reduced face velocities typically means a reduced volumetric rate. So it might be more friendly to an exhaust system that has limited capacity, or supply system that has limited capacity. Also, if you have a customer that was looking to increase from a 4-footer to like a 6-footer, a high performance hood might be able to work with the airflow or the volumetric rate that was used for that other hood, due to the fact that it's able to be ran at lower face velocities because of its containment properties. And then lastly, I want to talk about are application-specific fume hoods. There are fume hoods that are designed specifically for certain processes that are being taken place, or more specifically, specific chemicals that are being taken place in or being handled inside of a fume hood. And the first one is perchloric acid. If you have a customer that is using perchloric acid, it requires a special fume hood that is designed to fit on a mechanical system that has a washdown. And that is because whenever you're heating perchloric acid, it has a chance to condense in the ductwork, and as that condensation evaporates, it leaves behind something called perchlorate, which is highly explosive. So a hood that is on a washdown system, that washdown system is in the ductwork, and it will wash all of that perchlorate out, making sure that it's not allowed to build up into these hazardous levels of perchlorate. They will have stainless steel, which is the primary recommended material of construction, especially because you're heating perchloric acid oftentimes. But there are PVC versions of the hood as well if you're using other types of acids with the perchloric acid. So there's no such thing as a small amount of perchloric acid. If somebody's using just a little bit over a really long time, that can be enough to create a large amount of perchlorate buildup. So perchloric acid means perchloric fume hood on a washdown system. There are other acids that are not that operate similarly to perchloric acid, but are not as volatile, and they require different materials to create their explosive salt, I guess. And in those situations, you'd go with an acid digestion hood. They typically also have different materials of sash, such as polycarbonate or Lexan, which is compatible with hydrofluoric acid is oftentimes used in acid digestions, but it will etch glass. So perchloric acid hoods use glass. Acid digestion hoods have Lexan, because the perchloric acid will crack or craze the Lexan, but hydrofluoric acid will etch glass. So again, those acid digestion hoods will have a washdown and PVC and those Lexan sashes to make sure that everything's accounted for. There are also radioisotope hoods that are made of stainless steel, so they're again easily cleaned, as I mentioned earlier. But also sometimes in radioisotope applications, they're using a gamma radiation, and to handle gamma radiation or to protect the user from gamma radiation, it oftentimes requires this buildup of 2-inch thick lead bricks. If you know anything about lead, you know that it's very heavy. Well, the stainless steel integral work surface of those radioisotope hoods is conducive to holding that kind of weight. So all sorts of different application-specific hoods that kind of make it easy. If you have a radioisotope application, there is a hood for that. If you have perchloric acid, again, hood for that. All of these things are to be considered. I hope this was helpful. If anybody has any questions, I believe we have time now. I appreciate you listening.
Thanks, Casey. So while everyone is getting their questions all typed out, I do want to take over the screen for just a moment and show you guys the expert series. So LabConco is running a promotion, so you can find that in here. You will also be able to find some literature, web links, as well as videos, and you can take a survey. LabConco also has a room in the Thomas Center showcasing a few of their products, so you can easily get there by clicking on the lab section next to the expert series logo, and then clicking on Lab Conco. So in here are a bunch of other resources as well as their products. And back into the expert series, this talk will be on demand by tomorrow, so you will be able to find that here as well as all of our other past talks. All right, I'll hand it right back to you, Casey.
Great, thanks for walking through that. But yeah, we have a little bit of time for questions if anybody has some. I think I saw one in the chat, and I can read that one. The question was, does LabConco certify the newly installed fume hood, or is the certification performed by a third party? It's a good question. LabConco, we build the hoods, but we know people who certify. We don't certify them. That would be a conflict of interest, because if we were to go up to our hoods, we would obviously have incentive to say, yep, the hood's working great, perfectly, yeah. Or even be, I don't know, I'd say LabConco, but this would be any manufacturer would have potentially a reason to be easy on their hood. So third party certifiers are the best route. And if you have questions on the certifiers that are in the area of your customer, we know a lot of them, so we can help you determine, or we can give you some company names. Not necessarily that we would endorse them or anything, but we know about a lot of them that exist. Okay. There was another question, said, if we were to use both hydrofluoric acid and perchloric acid, what would be the best material for that? It's a great question. So if hydrofluoric acid is not compatible with glass, perchloric acid is not necessarily compatible with Lexan. There's a material of construction problem that occurs. And there are two ways to go about that. One would be two hoods. To have a hood where you'd handle your perchloric acid, and have a hood where you handle your hydrofluoric acid. Understand that's an expensive option, but it is one option. The other option, or the other solution, is for a customer to determine that, well, one of them is a worse case scenario than the other, and they will take caution to or take steps to mitigate the effect of the other in that application. So if someone were to use more hydrofluoric acid, they might determine that they'd prefer the Lexan sash, and their risk for the perchloric acid messing with it is less. If they have more perchloric acid, they might determine the opposite, and they'll go with the glass, but then decide that they're going to wipe down the glass, making sure that the hydrofluoric is not etching it at a great rate. There's no perfect material, but that would be the two options for those customers. There's another question. It says, we are sometimes working with high volumes of flammable solvents. Are there any special considerations that should be taken into account as it relates to fume hoods, to the fume hoods that we use these chemicals in? Another good question. It's again more about the materials of compatibility. So if you're using high levels of solvents, you wouldn't want a PVC hood. But if the concern is a possible ignition for that high level of solvents, then you would just want to make sure that everything that is in the vapor path is spark resistant from the front of the hood all the way through the ductwork and through the impellers of the fan to the top of the exhaust stack. If there is not a spark potential within that vapor path, then the risk of ignition is mitigated. Most fume hoods, especially LabConco fume hoods, they don't have a spark potential on the interior of the hood, because certain things like an FPA 45 say to not have electrical components like duplexes or anything on the inside. So just making sure that you don't create a potential where you could ignite that flammable vapor And then obviously, if you're in a lab that has a electrical classification like class 1, div 1, or something like that, that has a hazardous classification, meaning you need an explosion-proof hood, which is a fume hood that doesn't have any electrical on it, so it doesn't ignite a potentially flammable atmosphere. But if it was in that kind of space, you would need an explosion-proof hood with those modifications. Good question. For HCl, so hydrochloric acid resistant fume hoods, can it be resistant against nitric acid too? Also a good question. So especially because considering, like stainless steel 316 is actually decently compatible with nitric acid, but very much not compatible with hydrochloric acid. So in that case, the answer would be no. But with a, say, fiberglass reinforced polyester, FRP, yes, those chemicals are typically, or that material is typically compatible with those chemicals. Same with PVC. There's PVC chemical compatibility charts all over the place. You can always double check the materials. Most manufacturers, LabConco included, would also be willing, if you have a customer that has chemicals that they're unsure of, we can send out samples of any kind of liner that you can test on and make sure it's good for your applications. The last question that I have in the chat currently is, in the event of a liquid spill within a 4-foot hood, what volume of liquid would be contained within the work surface of hood and not overflow and spill out of the hood? That is a good question. Obviously, so in a little bit of background in LabConco fume hoods, the work surface has a spill zone. It's dished where if you were to spill something, you have enough of a dish to contain that spill, so it does not overflow and then come out the front of the hood. Generally, if you have a 4-foot hood, and I take a 4-foot hood, they come in different depths. So just generally speaking, a 4-foot hood designed for a 30-inch deep work surface would handle about 5.5 liters of chemical before it were to overflow. Considering a 4-foot hood is 5.5 liters would be a lot of liquid to be handling inside of a 4-foot hood. So that's generally pretty good. But yeah. Those are all the questions I see. Does anybody have any more questions? We have, I think, about 5 minutes before we're finished up here. We have a little bit of time. I see thank yous, and I thank you guys for listening to me. If nobody has questions, I don't know if I have the authority to end it, but I'll stick around for the other 4 minutes left. But yeah, thank you guys for listening. I appreciate it.
Yep. Thank you all for joining us. And if you have any other questions, feel free to stick around, and stop the recording now.